These three videos on the physics of space travel, as well as instructions for flying the 2016 Orbiter Simulator, are available in my book, Physics for Space Travel, available on Amazon.com. Okay, so in the previous video, I launched to orbit and acquired this orbit right here. So as you can see, it's not a circular orbit, and we know that because the eccentricity is not equal to 0. Okay, so there are very good reasons why we want to circularize this orbit before providing the thrust to create the transfer orbit and begin our journey to the moon. And let me describe what those reasons are. So why circularize the orbit of the spacecraft around the Earth prior to leaving the Earth for interception with the moon? Three reasons I came up with. One is so that there is actually a transfer orbit solution from Earth to the moon. Two, so that one can use the Hohmann transfer method, which is the most energy efficient method. And three, to provide timing departure from Earth to the moon flexibility. Why circularize the orbit? Well, there is an easy orbit solution and many different interception points in the moon's orbit around the Earth. Okay, here's an example. The spacecraft provides a thrust at this point, okay, while it's in the circular orbit around the Earth, and grows the orbit to this highly elliptical one, such that the interception point between the delta glider, right, and the moon is down here. Another solution, circular orbit again. This time, thrust is provided at this location in the orbit about Earth, and creates this elliptical orbit with the interception point here between the moon and the delta glider, right? The moon and the delta glider. So when the moon is here in its circular orbit around the Earth, the delta glider will provide the thrust here of sufficient magnitude such that it will intercept the moon at this point. Okay, so here is an initial orbit of the delta glider about the Earth, and where there aren't many optimal solutions or efficient solutions, I would say point A would be a solution, a possible interception point. I think the other ones are also possible interception points, but incredibly inefficient to try to grow that orbit to points B and C. Okay, so for circularizing the orbit, how does one compute the velocity required to achieve a circularized orbit? Okay, so the energy equation can be used to derive for velocity here. And here is the assumption. The apoapsis is currently 6.933 million meters. Okay, that's where the burn is provided. Okay, remember, apoapsis is further from the center of the Earth than the periapsis. Okay, apoapsis is 6.933 million, periapsis is 6.533 million. When the apoapsis is equal to the periapsis, you've got a circular orbit and eccentricity goes to 0. So the idea is to get the spacecraft here and provide a thrust in the direction of travel. That's a prograde thrust. And I think I've already mentioned that if a thrust is provided at the apoapsis point, the apoapsis distance won't change, but the periapsis distance will. It'll essentially grow this orbit. And with sufficient thrust, it will grow it to the point where the periapsis point will be equal to the apoapsis point. So this is before the thrust, eccentricity 0.0297. This is after the thrust. Now we have a eccentricity of 0.0004. Okay, and as promised, the periapsis distance, 6.929 million, is equal to the apoapsis point, approximately 6.935 million. The other thing for a circular orbit is the semi-major axis, which is essentially the radius of the orbit, SMA, is also going to be equal to the apoapsis point and the periapsis point. Okay, so how does one estimate the required velocity for this orbit? The current velocity is 7469 meters per second, and right now the delta glider is located here. You see that from the green solid line, located at the apoapsis point. So that's where the thrust will be provided. Okay, so this equation can be used to compute the velocity for this new circularized orbit. We're going to plug in the constant g, 6.67 times 10 to the minus 11th. Here's the mass of whatever you're orbiting. In this case, it's the Earth. This is where the thrust is provided, 6.933 times 10 to the 6th. That's the periapsis point. Minus 2 times the semi-major axis of the new orbit. Okay, so as I mentioned, this thing is going to grow such that the semi-major axis and the periapsis point are also equal to 6.933 times 10 to the 6th. So that's what I plugged in for A here. Plug this into my calculator, and I got a required velocity to acquire this new orbit of 7584 meters per second. So I provided the thrust at that point, and my final velocity was 7582. Just a teeny bit off, but definitely acquired a highly circular orbit, sufficiently circular to move on to the next step of aligning the plane and thrusting to the moon. Okay, so the next thing I'm going to do is I'm going to circularize this launch orbit. Okay, so as I mentioned, the thrust will be provided at the apoapsis point. That's this right here, this point right here. Circle with nothing inside. Here's the periapsis point. It's pretty simple. When you get here, I'm going to provide a prograde thrust, so that's thrust in the direction of travel, until the PER point is equal to the APR point. And when those are equal, this eccentricity will be 0, and we have a circular orbit. I'm not going to do the calculations. I'm just going to monitor these and cut the thrust when these two are equal. All right, so wait for this thing to come to a rest here, and then we'll get started. I'm going to time warp. Okay, so right now the Delta glider is here in the orbit, moving counterclockwise, so that would take quite a long time for it to get over here. You can hit the T button, and you can increase the time right here by 10 times. If you do it twice, it's 100 times, okay? I don't like to go much above 100 because essentially what you're doing here is you're skipping calculations. And certainly you can go 1,000 times for some period of time, but not for too long before the thing gets a bit unstable. Okay, so we're here at our closest approach. It's pretty tight, 6.46 million meters. The radius of the Earth is 6.38. Okay, so now you can see we're getting further away from the Earth. Let's look back at it. Okay, so now we're on the dark side, right? So the sun is set on this side of Earth. And again, we want to get to this point right here, the apoapsis point. This right here, the APT tells us the time until we get to the apoapsis point, so it's 2,900 seconds. Closing rapidly. So we're getting pretty far from Earth right now. It's a highly eccentric orbit. Okay, I'm going to start slowing here when I get to this point here. Okay, so I'm going to go to time warp of 10 times. Okay, so now I'm 429 seconds away. Speed up a little bit. Okay, so now I'm 240, 230, 22, 21, 19, 18. You can go ahead and start the thrust a little bit before you get there. You want to provide equal amounts of thrust on that side as well as the other side. I haven't done the calculation, so I don't know exactly when to fire before and when to fire after, but I'm just trying to get an approximation just to illustrate how this is done. Okay, so Control Plus on the keyboard gives you full thrust. All right, and as long as we're pretty close to the apoapsis point, I'm going to let the thrust continue. Once I get too far on this side of the apoapsis point, I'm going to kill the thrust, time travel around again, and provide the thrust again. If I get too far away from the apoapsis point in providing thrust, I'm not going to achieve my objective because the apoapsis point is going to start to grow. This thing is going to start getting asymmetrical. Okay. You can also time warp during the thrust, but definitely not more than 10 times if you're thrusting. So I'm gonna do time warp 10 times. Okay, so we're getting where's apoapsis? Okay, so I'm gonna kill it and come around again. kill the thrust. Come around the apoapsis point again. Eccentricity 0.0591. Okay, so we're going to try to get that a little bit lower. Time warp apoapsis again. Oh, I'm at 1,000 times. Wow. Remain stable though. 100 times. Okay, so again, that's the apoapsis point here. Slow it down here a bit. Okay, so I'm going to provide prograde thrust again. Try to get this eccentricity down to 0, which should get us to a APR equal to a PER. So I'm providing half thrust because I don't have that much further to go. I'll increase a little bit more. .0164, 0.0115, 0.009. Okay, now I'm going to start backing off the thrust. Okay, it's very good, very good. Oh, it's starting to go up. Okay, so I'm going to kill the thrust. Okay, so now you can see the PER point is 14.26 million. The APR point is 14.32 million. So we've got a little bit more thrust. Okay, so I'm going to fast forward. This thing is flipped. I'm going to fast forward to the APR one more time. Provide just a teeny more thrust, and that should bring the PER up to 14.32. And this should be almost 0. Okay, just about there. Time to apoapsis, 50 seconds, 40, 30, 20, 18. Okay, I'm not going to need much thrust, so I'm just going to get just a teeny bit. Okay, I'm going to try to get this down to 0. Probably won't be able to get it to 0 exactly, but... Okay, 0. I actually came back up a little bit. Okay, so now if you could look at the PER, periapsis 14.32 million, apoapsis 14.33 million, and the semi-major axis also 14.32. So as promised, those three are equal, and it appears to be almost perfectly circular, and eccentricity is telling us it's almost perfectly circular. Okay, so this thing is circularized. The next step is going to be align the orbit of the Delta glider with that of the moon. Okay. Before we can leave Earth to meet the moon, we have to align the orbital plane of this spacecraft to coincide with that of the moon. Okay, and right now, the inclination between the orbit of the moon around Earth and the orbit of the Delta glider around Earth is 22.78 degrees. Okay, so the question is, why does that need to be 0? And how do we go about getting it to 0? Okay, so I think this picture does a pretty good job at showing why we need to align the orbital plane of the spacecraft, okay, this plane right here, with the plane of the moon orbit going around Earth. There are 2 points of intersection between the orbital plane of the spacecraft, this is about 23 degrees, and the moon, okay? Okay, so say the moon is here and the spacecraft is also there. It would be possible, but very expensive from a fuel standpoint, to fire enough thrust in the right direction to fall into orbit around the moon. But they're going in 2 different directions, so that would be very expensive and very complicated to try to fall into orbit at these 2 interception points. Again, since they're going in different directions. Okay, a better approach is to align the orbital plane of the Delta glider about Earth with that of the moon about Earth. And now you've got many, many points of intersection, okay? And when the Delta glider does intercept the moon, they'll be traveling in the same directions. So the only thrust required is a slowdown thrust. Sufficient slowdown thrust will result in the Delta glider falling into orbit around the moon. It's quite simple, actually, if they're in the same orbital plane. Okay, so let's go back to the spacecraft, and I will demonstrate how to align the orbital planes. So the next thing I'm going to do is show you how to align the orbital plane of the Delta glider around Earth with that of the moon around Earth. Okay, so you're going to select here the align plane, multifunction display. You're going to select target, enter, and type moon, enter, and it brings up this display. Okay, so the Delta glider is here in its orbit around the Earth. That coincides with this position over here. And we want to get the Delta glider at this point called a descending node or an ascending node before thrust is applied. Uh, the ascending and descending nodes are the 2 points where the orbital plane of the Delta glider intercepts that of the orbital plane of the Earth. Okay. Um, and after I show you how to do this procedure, I'll talk a little bit more about why the thrust is applied at the ascending and descending nodes and the required configuration of the spacecraft prior to firing that thrust. Okay, so I'm going to first reorient the spacecraft such that its engines are pointed in the direction of the orbital plane. So the thrust will be normal, okay, NML plus, to the orbital plane of the spacecraft. So again, I'll talk about that in a bit, why that's the case. Okay, so I'm going to hit NML plus here. If it's DN, you're going to hit NML plus. If it's AN, you're going to hit NML minus. These are autopilots. Okay, so this the autopilot's automatically rotating the spacecraft 180 degrees, again, so that its engines are perpendicular to the orbital plane of the Delta glider. Okay, so now I'm going to time warp by hitting T, so we can get to the DN point a little faster to apply the thrust. Okay, this so right at the DN point is when we apply the thrust, and this instrument will actually tell you when. So engage thrust. We're going to go ahead and hit Control plus, provide full thrust, and the relative inclination is coming down. Yes. Okay, the idea is to get this below 0. Okay, so I'm going to time warp a little bit, and as you can see, it is coming down rather quickly. I wouldn't time warp more than 10x. It'll tell you when to kill the thrust. Should be providing that message shortly. We're at 1.2 degrees, 0.85. Okay, I want to start backing off as you get closer and closer to 0. You want to go ahead and start backing off a little bit. 0.42, 0.41. Now it says kill thrust. Okay, so the further you are from an ascending or descending node, the less impact thrust will have on the rotation of the orbital plane. So the next thing to do is to go to the ascending node. We'll try to get this down just a little bit more. Okay, so we're going to time warp to get to the ascending node. And it should only require probably a second or two of thrust to get this down to about, as close to 0 as we possibly can. The closer you are to 0, the better result when trying to intercept the moon. Okay, I'm going to turn off time warp, and if you recall, at the AN point, we need to be in normal position down. Okay, it's just going to reorient this. Because I'll show you why normal plus versus normal minus, depending on whether you're at the ascending or descending. I'll tell you why that's the case here in a minute. The other thing is TN says time to node for the nearest node. So when that's pretty close to 0, it'll tell me to fire the thrust. We're 130 seconds, 100 seconds or so. 9, 8, 7, 6, 5, 4, 3, 2. Okay, like I said, it's just going to take just a teeny bit of thrust to get this done. So say an engaged thrust. Okay, so I'm not going to put too much on because I don't want to. Too much thrust will actually result in the inclination going the other way. So it's 0.3, 0.27, 0.24, 0.18, 0.14, 0.04, 0.03, 0.02, 0.01. Okay, that's about as good as I'm going to get it. Okay, so mission accomplished. We now have a circularized orbit, 0.0073, and we have an inclination of pretty close to 0. I may make this a little bit more circular, but I'm going to go ahead and do that on my own time, not your time, since you already know how to circularize the orbit. The next thing I'm going to do is talk a little bit more about the physics and math theory behind aligning the orbital plane, and I'm going to reference my book to do that. So stay tuned for just a second. Okay, just previously I showed you how to rotate the orbital plane of the Delta glider to align with the orbital plane of the moon. And I mentioned that the thrust needs to be provided at the ascending or descending node. So here I'm going to explain what those are and why that is where the thrust needs to be applied. So if you recall, the ascending and descending nodes are where the reference plane, in this case, a plane that Earth moves in its orbit around the sun, intercepts the plane of the orbit of interest, in this case, the orbital plane of the Delta glider. So here's the orbital plane of the Delta glider, the blue plane, and the plane of this Earth moving around the sun is the red orbital plane here. Okay, so let's say we want to rotate the orbital plane of the Delta glider this way to align with that of the Earth's orbital plane around the sun. Okay, so the equation for torque is equal to force, in this case thrust, times r. That's the distance from the rotation point to where the thrust or force is being applied. And that's equal to the moment of inertia times the angular acceleration. Okay, so the moment of inertia for the spacecraft, assume it's just a point mass to keep it simple, would be mr squared. And again, here's the angular acceleration. Okay, so I can solve this for the angular acceleration by dividing both sides by m times r squared. And when I do that, this equation becomes this equation. Angular acceleration is equal to the force, or in this case, the thrust, divided by the mass of the spacecraft times r. As you can see, the further the thrust is from the rotation point, okay, in other words, the greater the r, the less is the angular acceleration, okay, which is acceleration in this direction. Okay, so that proves mathematically you're going to have more of an effect of an orbital plane change if the thrust is provided as close to the ascending or descending nodes as possible versus providing that same level of thrust, quite a distance away from those ascending or descending nodes. Okay, and you can actually test this for yourself by flying the Orbiter 2016 simulation and try to apply the thrust a fair distance away from the ascending or descending node, and you'll find that it doesn't have much effect in reducing the relative inclination between the two orbital planes. Okay, so in my book, page 94, I go into quite a bit of detail about this, what I just explained to you, and I also provide a quantitative example. And let's just go through that briefly. Let's say you want to change the orbital plane by, in this example, 13 degrees. Okay, that's the I here. V is the velocity before the thrust is applied. And this is the delta V required. Okay. So if you multiply 2 times the current velocity of the spacecraft before the thrust is applied, times the sine of the angle, the inclination angle changed, divided by 2, in this example, you get 1782 meters per second. Okay, so we know from a previous equation that delta V is proportional to thrust. In fact, the thrust is equal to the delta V times the mass divided by the duration of the thrust. Okay, so the delta V computed was 1782 meters per second. So that's not actually going to affect the speed or the magnitude of velocity of the Delta glider. And here's an example or proof. The velocity before that thrust is applied is 7871. Okay, then after this delta V or thrust is applied, the velocity is 7865, so it didn't change hardly at all. It certainly didn't change by 1782 meters per second. So the question is, why didn't it change? Here's a pretty good graph that explains why it didn't change. Okay, here's the velocity vector of the delta glider before the thrust. Okay, and here is the normal, right? Remember I mentioned that the thrust is normal or at a 90-degree or perpendicular to the plane of the orbit. So using addition of vectors, graphical addition of vectors, the final velocity vector is this direction. The final velocity vector after the thrust is equal to the initial velocity vector before the thrust plus the delta v, okay? And again, delta v is proportional to thrust. So there you have it. The length of the velocity vector did not change, okay? So the magnitude velocity doesn't change. In other words, its speed doesn't change, but the direction of the velocity did change. If you recall, velocity is a vector, meaning it has magnitude and direction. So it takes a thrust to change the magnitude of velocity as well as the direction of velocity.